Hello everyone, this is week number 6, chapter 2, and today we're going to look into the exponential function and its arithmetic properties and the proper definition of it. The lecture is outlined in the following way. First of all, we will derive the important properties of exp of x, and once we have done that, we will look at logarithm, which is the inverse function of the exponential series, equally important. And in the end, we are gonna make a little practical session and determine some handy rules of arithmetic. So we will discuss how to handle exponential terms in your equations and functions. In the end of the previous lecture, we already discussed that the derivative of x of x is x of x itself. And this inversely means that the integral of x of x dx is equal to x of x. I assume that most people watching here have a basic understanding of what an integral is. Of course, this is not a prerequisite of the course. If you don't know what an integral is, we will cover it thoroughly in the course later on. For now, you can just treat it as the inverse operation of differentiating. So we already know one fundamental property of the properties we're interested in. There are a few more, however. There's injectivity and surjectivity, there's invertibility and monotony, and we are interested in all of these features. We want to know does our exponential function have them or not, and if so, why? Okay, in the last lecture we saw that the limit of x towards infinity of the exponential series is infinity. This means that if we plug in x into our infinite series, we tend in the limit to get positive infinity. And in order to answer the question about monotony, so is our function monotonous, we have to first of all figure out how the exponential series behaves if x becomes really, really small instead of really, really big. Because if, for example, the limit when we go to negative infinity is also positive infinity, we could rule it out altogether. But once we figure out what the limit here on the slide is, we will have a base for making an argument for saying that we have a monotonous function at our hands. Turns out this is not that easy to solve. If we just plug in negative infinity into the terms of the exponential series, we are not really getting a conclusive result. So first of all, we have to derive a little rule to help us out. Let's first of all, before trying to figure out what the value of x of negative infinity is, figure out what is at x of 0. This is a pretty easy exercise. We just plug in a 0 for every x and it becomes 0. And the only remainder is our first term, which is always 1. So x of 0 is just 1. And now there is a little theorem which comes in really, really handy. And the theorem is that x of x plus y equals x plus x of y. This means that if you multiply two exponential terms, you're basically adding the arguments within one. And this is something which you can prove quite directly using the definition of the exponential series. So you just take the exponential series and plug in x and y. And if you feel confident, you can just do it as a small exercise to prove this theorem. We're not going to do it within the lecture. We can use this theorem to derive another property of the exponential function, which is going to be paramount for proving all the other properties that we are interested in. Let's start off with 1. 1 is the value of the exponential series of 0. And there is a different way of expressing the exponential series of 0. We can just express it as x of x minus x. Now, this kind of looks like a pointless transformation, but in mathematics, we'll oftentimes do pointless transformations in order to get to a point where things make sense. So, x of x minus x is kind of the same as x of x plus minus x. And this again, according to a theorem, we can express as x of x times x of minus x. And this is all still equal to 1. What does this mean? It means we can divide by x of x. So we get that x of minus x equals 1 over x of x. This means that if we have a value for the exponential series for a positive argument, we can get the value of the negative argument just by taking the inverse. And this is a very, very important property which we're gonna utilize right now. Remember our limit problem? We wanted to figure out what happens if we let x run towards negative infinity. And we can ignore this problem by instead looking at what happens for x running towards positive infinity, but not for x of minus x, but 1 over x of x. And this is now a question which is pretty simple to answer because, well, x of x goes to infinity for x towards infinity, and 1 over infinity has the limit of 0. So we know that our function, our exponential series, has the limit of 0 when x goes to negative infinity. And this is basically all the groundwork we need to prove strict monotony. We now just have to show that every x prime, which is larger than x, has a bigger exponential series value than its initial x. So this means if we take a random value x and we compute the value of the exponential series, if we go at some point to the right of it on a number line, we're going to get a larger value. And if this always holds, and we know that the first value is smaller than the last value of our exponential series, we know that we have strict monotony, right? So how do we go in proving this? Well, it is actually pretty trivial. We just take the exponential series of x prime, and this is just 1 plus x plus delta squared divided by faculty of 2 and so on. And here we see every individual term is greater or equal to the original term of x of x. So if we compare x of x prime with x of x, we see that every single individual term of x prime is either greater or equal to the values for x. This means that every single x prime larger than x has a larger value of the exponential series, and this yields strict monotony for x greater than 0. And since we have the identity we showed right before with the inverse relationship for negative arguments, we also know that the same thing is true for x smaller than 0. And thus we have proven that the exponential series is monotonous for every single real. Now, one important step for discussing bijectivity is that we have to decide on a domain and a codomain. And the codomain of the exponential series has to be R plus, so the positive real numbers, including 0. And this is very important because Otherwise, we violate surjectivity. Imagine we get a definition of the exponential series which maps from the real numbers to the real numbers. Then, pretty simply, the number -1 has no pre-image. There is no x such that the exponential series of x equals -1. And this would be a counterexample proving that surjectivity is not given. We avoid this problem just by defining the exponential series to map from the real numbers to r plus. And now surjectivity can be shown just by applying the mean value theorem, which I hope you dearly remember. So the limits of the exponential series for negative and positive infinity are 0 and positive infinity. And this is exactly the interval of our codomain, which goes from 0 to positive infinity. And since we know that the exponential series is continuous, granted by the theorem we showed in the previous chapter, we know that every single value between 0 and infinity has to have a pre-image. And every single value in the codomain has a pre-image. That's just the definition of surjectivity. Meaning, the exponential function is surjective. And injectivity is even easier to show. It follows directly from strict monotony. Injectivity just means that no value in the codomain has more than one pre-image. And if we have strict monotony, this means that the values of the exponential series are ever increasing. And since we're never going back, no image value can appear twice. And so since surjectivity and injectivity are given, we also can memorize the exponential series is bijective. But bijectivity yields another property. If you remember from the definitions we introduced in our chapter on functions, bijectivity is given if and only if invertibility is given. This means we can find an inverse function. And this begs the question, what is the inverse function of the exponential series? And we're just going to define it right here. We know how an inverse function is defined. So we are just going to define the function which does the inversion. So the inverse function is called the logarithmus naturalis, and it's denoted as ln of x. And it has the property that if we concatenate the exponential series with the ln of x, or we do it the other way around, it's commutative, we just get the identity of x. We want to talk formally about the logarithm. However, for the logarithm, we're not going to use a fancy exponential series to define it. And so in order to be able to talk freely about the logarithm, we are now first going to unify the formal definition of the exponential series, which uses a power series, as you remember from the last chapter. And we're going to unify it with the practical motivation behind it. So we're going to unify it with the practical idea which lies behind an exponential function. So take the following definition. We have a function f of x, which is a to the power of x. And this type of function, where we have a constant and it is raised to a power, a variable power, is called the exponential function, and an exponential function. And if we take the exponential series x of x, this just converges to the exponential function where our constant a equals Euler's number e. And then ln of x is just the logarithm with base of Euler's number. If we take another function a to the power of x, then the corresponding logarithm, which inverts the function, just has the base of a. And now, of course, all the questions follow. What kind of properties does the logarithm have? And in all practicality, more or less the same as the exponential function. However, a few of them are worth talking about. For example, the derivative. The derivative is one thing you should just memorize because it comes up quite often. If you derive the natural logarithm of x, you just get 1 over x. Other than that, the function has all the values that the exponential function has as well for all real values. Okay, now all properties of those functions aside, let's get practical. Let's talk about some identities which we are going to use when encountering exponential functions and logarithms. The first one is, we just said that we're going to use e and, well, e as a base for our exponential function and our logarithm. And this is certainly justified. For example, in the natural way that we define the exponential series to give us an exponential function, the natural base we get is e. And this makes a lot of sense because e is the only base for which the exponential function has the derivative of itself. Otherwise, the derivative does not match the initial function. But since e seems to be so powerful as a base, there is a pretty simple identity which allows us to transform any exponential function into an exponential function with base e. So if we get a to the power of x, this is just the same thing as taking e to the power of ln of a times x. And if we get a logarithm to base b of x, we can rewrite this in terms of the ln just by saying ln of x divided by ln of b. The second rule I want to show you is the multiplication rule for exponentials. So this is a very important rule which you should know and be able to utilize in algebra exercises, which is that if you multiply two exponentials, you can, instead of multiplying them, take them together and just add the arguments. And the same holds true for logarithms. The third property is taking the power of exponentials. If you take an exponential to another power, it's the same thing as multiplying the powers. Now, last of all is the rule that says that our entire operation right here is distributive. So if we get a times b to the power of x, it's the same thing as a to the power of x times b to the power of x. Obviously, we're not going to get into detail into proving all of these rules. If you're interested in this, consider it as a small exercise. It is not particularly difficult, but it just doesn't fit into the scope of the lecture right now. All right, I hope you are not left with any questions. It would be ideal if you were familiar with some of the concepts beforehand, but if not, I hope this lecture really helped you. A quick summary for all things we covered right now. We saw that the exponential series converges towards the exponential function e to the power of x. And this means that the exponential series, so the power series with the function 1 over the faculty of n, is just the formal mathematical underlying definition of the exponential function. And we saw that if we pick the right domain, this is an extraordinarily well-behaved function. Like, child of the year well-behaved. Just incredible. It's invertible and bijective, it's continuous, differentiable, especially infinitely often differentiable, and differentiates to itself. It's strictly monotonous. Like, what else can we expect from a function which is not the identity, right? Then we look at the inverse, which is the natural logarithm of x, and we saw that it has similar properties and is also very well behaved. And in the end, we looked at the handy rules, which we use for dealing with exponential terms and equations. You're free to use any of those rules in any sort of arithmetic exercises which you're going to encounter in the future in this course or any other place. Thanks for listening.